Great. Hopefully everyone can hear us online. Where's our online thing? Okay, if you can hear me online, why don't you put a chat in the window for me? I've got a few folks in there right now. Mike says it's registering, so I'm going to go with the assumption you guys can hear us online. Yes, welcome all. For those of you who have never attended one of these events, you are attending the First Friday Boise State Physics Astronomy event. Welcome. My name is Brian Jackson. I'm a professor in physics here at Boise State. These events take place on the first Friday of every month at 7:30 p.m. Mountain Time. We're doing them in this room right now. Hopefully we'll be able to move back across to the other room. I don't know if you've looked into the other room, but it's completely gutted. There aren't even like chairs or there's nothing in there. So hopefully that'll be open because we're going to start school here in a couple of weeks. We've been doing them in this other room, but they take place at 7:30, always on the first Friday of the month. So this is August, the first Friday of August. Whether school is in session or out, we have these events. We have scheduled a bunch of really great talks for you in the fall here. I'm going to turn the lights off just a bit so you can see them better. So here's our fall schedule. It should be really great. So first off, we're going to have in September a friend of mine, Professor Matthew Pasek, is the University of South. Oh, that's the University of South Florida. He is a meteoriticist. So if you have a strange rock that you want to know whether it's a meteorite, you should bring it for that event. It can identify it for you. Then we'll have Professor Guy Worthy from Washington State. We'll have someone from the Central Idaho Dark Sky Reserve in November. This is going to be a really great event. We're going to have some of the members of the Dark Sky Reserve board come out, and they're going to do a little education about light pollution. If you've been out to the Dark Sky Reserve, that's right through Central Idaho. That's basically between Stanley and Ketchum. So probably many of you have been out there. You may not have realized though that it was a Dark Sky Reserve, gold tier, the very first gold tier Dark Sky Reserve in the United States, in fact. So it's a very dark part of the United States. But if you're ever out there in Stanley and you happen to look out to the southwest, you might notice this glow on the horizon. Well, that's Boise. And so they're going to come out and talk to us about the effects that we're having here in the city on the reserve there, and just all the really great stuff they're able to do out in the reserve in terms of outreach and education. And then in December, to round off this the season, we have Dr. Angela Dappermal, who's an expert in Martian geology and astrobiology, and she's going to give us a talk about Martian mud volcanoes. Probably didn't know that there are mud volcanoes on Mars, but there are. So she's going to talk to us about that. So again, those happen every first Friday of the month, 7:30. If the weather's clear, we go up to do stargazing after the talk. I'm afraid if you probably noticed it's very cloudy out tonight, so we can't go. But if you want to stick around and just go up to the observatory, it's beautiful up there. So we're happy to take you up there afterward. These are also live streamed. We're actually live on YouTube right now, hopefully. No, no one has chatted, but we are live on YouTube right now. So if for whatever reason you can't make it down here, go to boi.st/astrobroncos live, and you can see the live stream from there. These are donation supported. Many of you, in fact, have given to support these events. And so if these are the kinds of things you like to see, feel free to donate what you can. Okay, great. And with that, I would like to introduce our guest speaker for this evening. We're very fortunate to have Professor Katie Devine here from College of Idaho. Professor Devine got her bachelor's degree in physics from Carleton College, followed by a PhD in astronomy at the University of Washington-Madison. If you know anything about astronomy, you know that UW-Madison is a really good school. That's a really strong astronomy program. What's that? What did I say? Oh, excuse me. And from that part, my wife's from Chicago, so UW means. Sorry, University of Wisconsin, forgive me. She joined the College of Idaho as a professor in 2009 and is now the chair of the department there in physics. Is that correct? Not to bring up any bad memories. And so she's going to talk to us tonight about her research on star formation. And let me switch over to her presentation. Let me see. Right there. Excellent. So let's give a very warm welcome to Professor Katie Devine. The camera will follow you.
Okay. Thank you very much. I'm going to trade places with you. So I was not quite sure what the background would be. So I know some well-versed astronomers, and we have a first grader. So I'm going to try and hit somewhere in there. But if you have any questions, I've left some time at the end, but also feel free if you want to pause and talk more about something, or you can give me one of these if you want to talk less about something, I guess. Just let me know. Thanks so much, Brian and your team of grad students, Bourgeois, Justin, yeah, and Haley and Sierra. I met some of you. Thank you guys so much for putting this on. This is a really nice event for everybody. So, and thank you all for coming. So as Brian said, I am from the College of Idaho. Today I'll be talking a little bit about a project I've had going on for a couple of years. But first I kind of want to get you interested in what I study. So why do you care? So a lot of astronomy is centered on origins. Where did we come from? How did the universe, how do you start from a big bang and build a universe with galaxies and solar systems and planets like we have here today? And understanding how stars form is an essential part of understanding how you get from a big bang to where we are now, because stars are a basic building block of galaxies, and how stars form, that process of star formation, can actually impact the galaxies around it. And so star formation itself has a really big impact on galaxy evolution, and that in turn kind of changes and shapes things. Another reason star formation is exciting is because when stars form, they form solar systems around them and planetary systems around them. And so if you are interested in how you get to a universe that has life in it, star formation is an important part of that as well. So today I'll be talking about my research looking at a new tracer of star formation known as yellow balls, and we'll talk about the goofy name, don't worry. And I'll talk about the critical role that people just like you, so anybody with an interest in astronomy and access to a computer, have played in their discovery, as well as the role that astronomy students in the classroom now can play in the next steps for understanding these objects. So if you're enjoying this object here, oops, you guys are seeing my presenter view. That's real slick, Katie. Brian, you were just gonna let me do that? Let's see. Well, you guys we'll just go with it. I know what I'm saying. It's just, I always like to, so those of you who are students, I always like to have my first slide scripted because it keeps me from being nervous. And now you know the thing behind it. And now I also forget numbers. And so 13,000 light years in the names of stuff. So if I'm not allowed to use it, I might have to cheat on the notes. So nobody asked me exactly how far things are away if I can't crib off my notes, because I can barely remember my own phone number. Anyways, this is W33. It's a star forming region in our galaxy. And this is what I'll be talking about in the center here. These are what we are talking about as yellow balls. And so I think with that in mind, before I get into a little bit of the science, though, I want to give you guys a sense of where the data that I'll be showing you come from. And so this is an artist rendition of our Milky Way. Anybody have an idea? I'm not an astronomer, but somebody else who's just kind of does this casually, of why this can't be a photo of our Milky Way? Well, we're not quite the center. We're over here, but yeah, we live in it. And to get this far away from a galaxy, you need to be traveling at the speed of light for hundreds of thousands of years to get a good picture. So this is not a camera, because we have never been able to put a camera outside our own solar system, let alone far enough away to take a picture. So this is an artist rendition of our own galaxy. And like, as you pointed out, so we're near the center, we're offset here, so that we're in this outer spiral arm. Here's our sun. And if you were to take this galaxy, this spiral arm galaxy, which is about 100,000 light years across, just to give you a sense. So light traveling for 100,000 years from something over here would travel to that far. Oh, that's okay. Well, then they didn't see my goof. That's good. Excellent. See, now it shows to this one. No, that's okay. Oh yeah, you can see me up there too. Doesn't know who to follow though.
Yeah, it's
Any questions so far while we're killing time? I think I know how to fix that. Are we good? All right. I'm going to, well, now I don't know how to end that. There it is. Hide presenter view. Okay. hopefully that didn't just ruin whatever Brian had set up. So I assume he'll come running in again if it. So all right, so you had that big spiral galaxy, and we were looking at it down. We were looking down on it, and now if you take it and rotate it so that you're looking at it edge on, this is a spiral galaxy seen edge on, and so we're looking at a galaxy very similar, not our own, but very similar to our own, but rotated. So it's basically like you can look at a frisbee this way, or you can tilt it and look at it side. And you see all this dark stuff in there. Why is it dark? Where are all the stars? Why is the center of a spiral galaxy dark? There's dust there, exactly. So there's a bunch of stuff there, and it's blocking the light. So it's not that there's nothing there, it's that there's a lot of stuff there. There's a lot of dust there that's blocking the light from behind. And when you look at a galaxy in optical wavelengths, so the wavelength of light that you can see with your eye, if there's dust in the way, dust blocks light very effectively at optical wavelengths. But now, this is our own view of our Milky Way. So now we're in the plane of our own Milky Way. And you'll notice that because like you pointed out, we're inside the Milky Way. We're in the spiral arm looking into the center of our galaxy. So instead of being far away in space, looking side on, you're inside the galaxy looking side on. But you see a very similar effect, right? You see that darkness. So this darkness is not the absence of material, it's dust in our Milky Way. And this is the type of view you might see if you were someplace with really, really good dark skies. And so if you're able to make it up to the dark sky reserve, you might look up and see the Milky Way on a really nice night. And you'll be able to see those dust lanes even with your eye. Probably not at quite this level, but you would be able to see them. All right. So the type of, see if I can put this where it won't quite. Yeah, well, that I think we're supposed to, well, let's see. I'll make it subtle down there. So the type of light that I use is not actually the optical wavelengths. So for those of you who have learned about light before, you probably know that there's the visible light that we can see with our eyes that gives us colors, right? So the longest wavelength visible light is red. It goes all the way down to blue light with the shortest wavelength. But here I'm showing the electromagnetic spectrum here. And there's a lot of other types of electromagnetic radiation, fancy word for light, that we can't see with our eyes, right? At the very shortest wavelengths, we've got gamma rays and X-rays, ultraviolet, then we've got visible, infrared on the longer wavelengths, so redder than red, right? Longer than red, infrared, microwave, and radio. And I work mainly in these longer wavelengths because longer wavelengths like infrared and radio are ideal for studying star formation. Stars form in clouds of dust and gas. And so to form a star, you have to start with a big cloud of dust and gas, and some areas of that cloud get denser than others for whatever reason. It just, usually there's a shock or something, but we'll worry about that another day. They start to collapse. And as as they collapse, they get hotter and denser. Eventually, if there's enough material there, the center of that hot, dense object can start fusion, warms up, glows, and there's a star. That is a highly simplified version. There's a lot of questions still about star formation. Otherwise, I wouldn't have a job or a research program. But what you need to take away from that is stars are forming from these big clouds of dust and gas. And so they're still inside an area of a lot of dust and gas. And as you know now, most of that dust blocks light if you're looking at it in optical wavelengths. And so if you want to be able to look down into those clouds of dust and gas, you're going to need longer wavelengths. The reason for this, let's see if my little animation will work here, is scattering. So I don't know if you're familiar with the term scattering, but this is kind of the physics of why the sky is blue and sunsets are red. So shorter wavelengths of light are scattered by small particles more effectively than longer wavelengths. So shorter wavelengths, bluer light, come through into our atmosphere. They get scattered by particles in our atmosphere, and you get a blue sky. At sunset, when the light is traveling through a lot of atmosphere, especially, luckily, knock on wood, we haven't had a bad fire season yet, but if we do get fire smoke in the air, it gets even redder because there's more particulate in the air. Scatters all that blue light away, and all you're left with is the longer wavelength, the red. So this is a very similar thing to what's going on when we're using infrared to look into clouds of dust and gas to see the star formation there. If you were to look at the plane of the Milky Way, this image is actually getting a little bit dated. It goes all the way back to the time when astronomers were really obsessed with using comic sans on everything. We went through a decade there where it was our favorite. But this shows Milky Way surveys. So in the early 2000s, there was a big push to start surveying the plane of the Milky Way at multiple wavelengths, and then comparing those data sets, which is great. And it produced so much data that a lot of the work I'm doing, all the work I'm doing right now, is actually writing off a lot of those surveys still. So this is the plane of our Milky Way at multiple wavelengths. The top 3 are all radio wavelengths, looking at emission lines from different molecules in space. Actually, the top one, I guess, is continuum, but this is radio continuum, hydrogen, more continuum at a shorter wavelength, more hydrogen. And then we start getting into the infrared wavelengths. And what you see here is the plane of our Milky Way, instead of being blocked like it is in optical, is glowing, just glowing with light in the infrared. And if we go forward in time, oh, by the way, this headline, I don't know if any of you read Slate, but it's my morning coffee, what's going on in the world. And this headline popped up on Slate, what was it, just last month, and it made me go, oh, don't tell people James Webb data is fake in any way. But it was interesting, and it's worth pointing out now because some of the images I'm going to show you are suddenly going to shift colors. And so since I am showing you images of light that your eye can't see, keep in mind, right, that these images, if you were to look at any of the infrared objects with your eye, they wouldn't look the same, right? So this is light that we can't perceive. And so the way we make images of it is to take the data. So we take pictures with our instruments and then assign those different wavelengths of light, the images that we've taken at different wavelengths, different colors. And we can stack those to make 3-color false color images. So they're called false color images. I object to the word fake. We say false color. But I mean, that kind of, if you look at this, so if you look at that mid-infrared image there, or the infrared image there, that means that if you looked at this with your eye, it wouldn't look pink. It would look like this, right? So these images are all false color images. And as the author says, and that's okay. That's kind of the point, right? But that will become relevant. The color choices will become relevant when I tell you why these objects are called yellow balls. They're actually infrared. Okay, so we're going to jump forward in time from these surveys to this survey here, which is the Galactic Legacy Infrared Midplane Survey Extraordinaire, or GLIMPS. It was one of the legacy programs on the Spitzer Space Telescope, which launched in 2003. And the survey itself ran from 2003 to 2013, so 10 years of taking images. And there are, this is where I had my numbers to crib, some millions of pixels and images. It took years and years to get all this data. When printed at full resolution, so if you were to print these out so that they looked before they became pixelated, they line up basically a big conference room hall basically along the way there. So I'll show you in a second just to give you an appreciation for how much data is in here. Just to give you a sense of what you're looking at over here on the edge. So remember, we're the sun. We're circling the sun right here. And this is the survey of the galactic plane as a 360 basically from our point of view here. So you can see which part of the galactic plane is being imaged here on this side, this column right here. And the reason we don't image above and below is because we were interested in the galactic plane. There are objects above and below, but this was really looking at the dust and gas in our own galaxy instead of the objects above and below our galaxy. Okay, so here is just to give you a sense of what is in the GLIMPS data and how much data there are to look at. So what we're looking at right now, you can play around with, especially those of you who are following from Zoom at home. Nobody's going to catch you playing around on a different web browser. But spitzer.caltech.edu, zoomable glimpse-WWT, which stands for Worldwide Telescope, has an interactive for this data. That's a lot of fun to play with. And so what's being shown here on this image right now is an image of the Milky Way plane as seen in optical. And then these red lines here are just to draw your eye to some of the zodiac constellations. So this is Sagittarius, Scorpio. So if you go out and look in the southern sky tonight, you'd be able to see those constellations. So just to give you a sense of where the galactic plane is in relation to some of those constellations you can spot. All right, I'm going to start this little animation. And the first thing it's going to do, this was a screen grab, so this was just me playing with this at home. So you can go over, and I toggled a little bar to turn on the infrared. So there's the glimpse data overlaid on the optical image. And now we can zoom in. So just to give you a sense of zooming in on that data, you'll see things start to come into focus. For the astronomers in the room, the pixel or the resolution is about 3 arc seconds on the 8 wavelength. So that's the longest wavelength shown here is about 3 arc seconds. It's a little bit better for the shorter wavelengths. So that pink emission is 8 micron, so mid-infrared light. And now I've zoomed out, and you can see that we're going to zoom in on a different part here. And so I'm just going to take you on a little bit of a tour of the galactic plane. And you can go ahead and pay attention here, because I'm going to ask you on the next slide what you noticed. So are there any features that jump out to you? Imagine me in 2004 when we first started getting this data. And it was just the whole glimpse team. I was on the glimpse team. The whole glimpse team was sitting around being like, what are these objects? What's that? What's that? What's that? So see if you have that moment here. Is there anything that's catching your eye? And I will ask you to chime in a second. Just to give you a sense of what you're looking at too. The blue light is the shortest wavelength. So all those blue dots are stars. The 8 micron light that's glowing in pink there is primarily being emitted by tiny, tiny dust grains known as polycyclic hydrocarbon, PAHs. Thank you, aromatic hydrocarbons. And so what those are tracing, or what the 8 micron, the pink glow is tracing, is you can think of it as like smoke in space, fine grains of dust. See some dark spots? It's actually emitting. Yeah, it's emitting. So the dust grains emit. So those PAHs actually have not emission lines, but emission bands. And one of the emission bands is right at the 8 micron filter that was on glimpse. And there's a very similar wavelength band on the MIRI camera on James Webb now. All right. So that's at the end of it. Okay, so what did you notice? Anybody want to volunteer any features they thought looked cool? Yeah, lots of blue dots at different sizes, lots of stars. There are people who love those stars. I'm an interstellar medium gal, but I will give you, stars were cool. And one of the really interesting results that came out of this, so one of the things that they did with the glimpse survey initially was to measure the light at all the wavelengths for those stars and use those measurements to determine that the galaxy has a bar in it. So there was a group that said, yeah, let's play with the stars. I wasn't part of that group, but some very cool stuff came out of the stars.
I did notice once compact object looked like the sun was very, very red.
Oh, yeah. So very compact red object. Yes, I like those. Anybody else? Ooh, spots of green and spots of pink. Yeah, some different things there. Do you guys see anything that looked like this? Bubbles. That was one of the things that really jumped out to the early science team that they weren't expecting. Was there were lots, I mean, they were ubiquitous. They were everywhere in the data, was lots of these bubble-like features. So many that a single astronomer with their grad students could not catalog them all. And so that becomes very important here in a second. There were also, did any of you notice these kind of dark filaments in here? What does dark mean again? Does it mean there's nothing there? Yeah, there's lots of dust. And so there's these really highly dense dark filaments that are called infrared dark clouds. Those are actually what I did my thesis on. So those were interesting enough for more study there. We think they're probably the sites of star formation eventually. Who was it that said the compact objects? So the compact glowing things and the green things? Yes, those also jumped out to people. And so there's been all of these objects. And the neat thing about having a survey of the entire galactic plane is that you're not looking at just one of these objects. It made it possible to identify a bunch of them. In fact, it kind of made it so that there were too many, right? There was too many objects for one person to just handle them all. And so around 2010, the glimpse team was invited. There were people on the GLEMS team who were invited to participate in a citizen science or people-powered research program. So the Xenoverse platform, xenoverse.org, has developed around people-powered science. It's a great platform for scientists, not just from astronomy, but from all areas of science, who have a lot of data that is very hard to automatically go through and find the things you're interested in. So a lot of projects like identifying wildlife, transcribing old handwritten letters into typed works, finding galactic bubbles in infrared data, and things that a human eye does a lot better job at than a computer. And so just to give you a sense, especially if there's any educators or people who like to do science for fun on the weekends, I know you're out there because you're here. So this is, I'll just do a quick tour of the current Xenoverse project. So if you click on the projects, you can go to a menu and you can see there's Chicago wildlife, seafloors, deep sea explorers. A lot of science teams now figure out a way that people can help them with their research and post their work on this platform. So, well, you can sort it by, if there's any teachers in the room, you can sort it by topic. So you can go to the space topics and see all of these citizen science programs centered on space. I use a lot of these in my intro astronomy class. My students love them. And then just to give you a sense, I'll back up here to give you a sense of what one of these looks like when you go to the project. Typically, you'll go to, sorry, it took me, I waffled picking one when I was doing my screen grab. I should have, let's go to, the tutorial. So if you click get started, almost always there's going to be some sort of tutorial activity that's short and sweet and trains you in what the science team is looking for and then what you're supposed to do to help them out. And so whether it's counting squirrels in Chicago or bugs on the seafloor or disks around like other planets or other star systems, you can be trained in a few minutes enough that you can actually help a real science team. And the reason these programs are so effective is because they need a lot of people helping. And you shouldn't panic about doing it wrong, because a lot of people means that if you make a mistake, but 6 other people look at the same thing, mistakes get canceled out. And so it's a lot of time intensive, but the nice thing is thousands of people want to do this and are willing to help out with the programs. So the Milky Way program, or the Milky Way project, was developed in 2010 as a way for people to look through that immense data set coming out of GLEMS. And they were originally tasked with finding those bubbles. So the group, all you had to do as a citizen scientist was to click on the bubble and draw a circle or an ellipse showing where the rim was. And then this shows the result of thousands of people looking at those bubbles here. So you can see this kind of ghost halo out here is fewer people, and then where it's really dark means most people found that bubble there. And then the aggregate result is here. And so this was used to produce a catalog of galactic bubbles. And they've done a lot of validation to show that people are detecting real bubbles and not just fake features. But there was an interesting result that came out of this. By the way, remember the whole thing about false color images? This is a lot less pink than those other images I was showing you, but it is the same data. It's just that instead of 8 micron being assigned the redder color now, it's being assigned the green. And so this green here is that dust, that really fine dust, like the smog through space. And now red is being assigned to an even longer wavelength, 24 micron, that traces warm dust and gas really well. And so one of the signature or hallmark signs of an intergalactic bubble is a glowing rim of PAHs that are probably being excited by a star on the inside, and then warm red dust in the center. So that's what a galactic bubble looks like. So that was just to make sure I remembered to point out the false color change here. But people started noticing that we were looking for these bubbles, but often near bubbles, there were these things, these little objects here. So classic bubble, here's a bubble, here's a bubble, but what's that? And what's that? And what's that? And so the neat thing about these citizen science projects is the people that get really into them have an opportunity to actually have a chat feature and talk to the scientists behind the scenes. And so one of the early users says, what is this thing? Does that get classified? And then the scientist said, if you're talking about the hashtag yellow ball, blah, 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 and the name stuck. So here we are with yellow balls. And And so the scientists that were supposed to be looking for bubbles also started flagging all these yellow balls in the images. And they flagged a couple hundred in the original Milky Way project. And our science looking at galactic bubbles actually gave us some clues about what those yellow balls probably were. We knew that the green emission was that glowing pH emission, so probably being excited by an ionizing source, a hot star. And the red was from dust, we knew the red emission was from warm dust. And so green plus red makes yellow in these false color images. So it was probably a really compact, an area where the ionizing pH, the ionized pHs and the warm dust were overlapping. So it was probably a really compact star forming region. And this is just a little bit more of the blog post in 2015, just to give you a timeline here, talking about the citizen science discovery that was just a serendipitous thing by not a professional astronomer, but somebody at home who was just paying really good attention to the images they were looking at. And so the initial hypothesis was that probably you would start out with an infrared dark cloud, get a star forming in it, move on to having a yellow ball that would then eventually have a massive star and that would expand out. So they thought they're probably baby bubbles, some baby massive stars. And I'm not going to make you read the whole abstract from the first paper. I just like the title because it was literally what are yellow balls. So, and then forward in time here, the Milky Way project, they realized from the initial project that had identified all these bubbles that they still had some questions and there were new things that they had missed in the first release and people still wanted to play with the data. So they revised the citizen science project and let people look for not only bubbles, but also they gave them a tool so that they could indicate places where the bubble rims were broken. They could identify objects like bow shocks, which were another feature. And we actually trained them and asked them to look for yellow balls. So this is a new page from the tutorial telling them what yellow balls look like and giving them a tool to mark yellow balls. So it wasn't just people that were paying attention and marking them through serendipity, but intentionally looking for them. And from this second release of the project, there were over 15,000 volunteers that participated in this. And they did 241,000 classifications, just to give you a sense of how, this is just people volunteering their time to look through data. And this is far more than you could ever expect any grad student to do. So it's wonderful contribution. And the volunteers found over 8,000 yellow ball candidates throughout the full Milky Way project, or the Milky Way plane. And so these are just an example of some of the sources that they flagged for us. So then we have the question of, now we know where thousands of them are, but what are they really? So we have some evidence that they're probably massive star formation, but can we do better at looking at the stellar content and the physical properties of these objects? So really getting more specific. Exactly how massive are they? How much light are they giving off? What kind of stars are going to form out of yellow balls? We think they're massive, but we know that not all of them are going to be massive. So can we get more specific than that? And so my colleagues and I took this and did a pilot study of about 10 degrees of the Milky Way plane. So remember, it's a 360-degree survey. So we took 10 degrees of it. And that had about 518 yellow balls. We basically developed methods for figuring out the masses and luminosities and distances and all these things that would help us understand more precisely what's going on in each and every yellow ball. Yeah. Sure, yeah. So, yeah, no, how do we do it? Yeah, no, so there is in the, for those of you who have thought about astronomy, when you look at the night sky, it looks like a planetary, like a dome, right? It's a two-dimensional. So trying to figure out that third dimension of distance is actually really hard. And so the way that we do it for this is not one that you would have heard about in an intro astronomy classroom. It's actually something that uses the kinematic model specifically of how the galactic plane rotates. And if you know that you are looking at something that is in a spiral arm, like a star forming region, then this method works really well. And so all you need to do is find an emission line. We used carbon from the carbon surveys, and we were able to find the velocity, how fast so the Doppler shift of the carbon cloud, and then use that information to match it to a rotation model and get the distance. Yeah, it's very cool. And it's a method that's been around for a while, but there's a group that's done it more precisely. And so they've got Bayesian statistics worked into it now. Anyway, my students ran the show on that one, and they've found the distances now to over 2/3 of the 8,000 sources. So she's pretty much done with the distance part. Yeah, Theodore, did you have a question? Okay, can it wait? Yeah, yes, exactly. So these lots of green dust near. So yeah. So that's the green next to the red is that hallmark signature of the bubbles. And so when you get that green next to red, those are galactic bubbles, indicating active star formation of massive stars. Good eye, good eye. He's the smart one. So we were able to get the physical properties, did a pilot region. And from this pilot study, the biggest thing actually that we found was when we were more precise, that first paper had claimed a lot of these are baby bubbles. They're probably young massive stars. Well, it turns out that that was only true for about 20 to 30% of them. And so a majority of yellow balls that were found by volunteers actually aren't going to go on to form stars that are going to be big and massive enough to blow these big galactic bubbles out in space that you were pointing out here. A vast majority, 2/3 or so, are probably more like intermediate mass stars that go on to form things like a Herbig AEB nebula. And so these objects are considered to be possibly a missing link between lower mass star formations, so stars like our sun, and massive star formations, so things that are like 8 to 10 times the mass of our sun. And so we have a fairly good model for the lower mass star formation. Things kind of fall apart when we try and model massive star formation. And we don't have a lot of observational data that links the two. And so there's a really good chance that we are looking now at a data set of thousands of objects potentially are kind of this missing link tracer. So we should probably look at them in more detail. But there are thousands of them, and that 500 source sample actually took a lot of time. So now the big science questions facing us are, how do the properties of star forming regions vary? So if you go outside of that 10-degree region and look at the whole galactic plane, do the properties of star formation regions change as you go to different galactic environments? So in the outer spiral arms, closer to the galactic center. And also, one of the kind of stretch goals for the project is there a way that we can relate these colors, the infrared colors, to the physical properties that we're also studying? This one's a little in the weeds, so I'll gloss over it, but I know there's astronomers here, so I can go into it in more detail at the end if you want. The technical challenge here is that measuring the light coming from these yellow balls at different wavelengths, so at the different color filters, is pretty time intensive. As the gentleman in the front pointed out, there's a lot of stuff going on in the galactic plane. You guys probably noticed this, right? That it's not just nicely like star, star, star. The people in here that study stars, you guys have it easy. You just measure it, you put a Gaussian profile over it, and you measure the light coming off of it. But we're looking at these objects that are not compact. They're not just point sources. They have structure to them, right? So the yellow balls are not just round. We'd like them all to be, but they're not. They have some structure, and they're sitting on this really complicated galactic plane background. And so how do we determine how much light is coming from the yellow ball and how much is coming from all the galactic stuff that's going on behind it? And so my students developed a tool to do what's called photometry, measuring the light off these objects with a galactic, by subtracting the galactic plane background. So I'll show you a sense of how this works. It's written in Python, like the code Python, but it's the same as the snake, same name as the snake. Let's see if I can get this to run. And so the way that you make this code work is you find the yellow ball in the center, and then you click around the edges. And so you're telling the program where the edges of the yellow ball are. And then it uses this mask here to remove it. It does an interpolation over the background and then gives you a background subtracted yellow ball only image. And there's some other stuff going on here in the code too, where you can tell it if there's anything else that you want to record about the object. But this photometry for every source has to be done on all 3 colors in that 3-color image. In fact, there's even a 4th wavelength that we've added. And so for each yellow ball, you have to click around it 3 or 4 times to get the photometry done. So it's very time consuming, but as you can see, it gives a very effective background removed source here that just lets you measure the light that's only coming from the yellow ball and not all the other stuff in the image. but it's time consuming. And we have thousands of sources to work with. So what do we do? And that's where the Periscope project comes in. So Periscope stands for, this is a new acronym, astronomers love their acronyms, People-Enabled Research, a yellow ball survey of colors of, what's the O stand for? I'm gonna have to go back to my main title here. It's a survey of the colors of protostellar environments. Oh, I think it's of protostellar environments. So our project is asking people-enabled. We're going to ask students, classroom students. And the reason we decided to go a little bit different than the traditional people-powered research where it's open to anyone is that photometry is actually kind of tricky. It takes a little bit of training. And so one of the feedback or one of the pushbacks we got from granting organizations when we started talking about we could do a citizen science project with this was, will the average user at home really be able to do the photometry without much training? And we were like, well, we actually don't know. The other thing that's a little different about this citizen science project is that it, as you noticed, runs on Python code, the code, not the snake, which makes it a little bit technical. It's not as easy or as user-friendly as a lot of the Xenoverse citizen science projects that show you a static image and just let you draw things on top of it. And so this does require a little bit of scaffolding, a little bit of hand-holding, but it seemed like the perfect match for an astronomy classroom where you're trying to integrate authentic classroom undergraduate research experiences that can be tailored into the existing curriculum without throwing out a whole class's worth of material. So instead of doing an activity where they're going to be measuring the light of stars hypothetically, why not let the students actually measure the light of stars and contribute to an active research program? And so we've developed a free browser-based Python code. And so the thing I was showing you before actually lives on the internet on cocalc.com. Anyone with a login that has the teacher material can get into it and copy the code over and run the photometry code. So you don't need to install Python on your computer. You don't need to debug all the installs. It just works for anybody who needs it. And we've also then developed an adaptable student activity for integrating this activity into the existing astronomy curriculum. So for those of you who have ever taken or taught an Astronomy 101 class, one of the things that's really usually talked about in the core curriculum is the HR diagram, how you sort colors by their temperature and how much light they give off and the patterns that emerge, and then how you can use those patterns to tell you stuff about the stars you're looking at. Astronomers in research often use what's called a color magnitude diagram, but it's the same basic idea. You're measuring light at different colors and you're sorting them on these graphs and looking for the trends that emerge to tell you something about the stars. Not quite as pretty in the infrared as your typical textbook HR diagram, but it has that same sense of letting students plot their own data, compare it to known data sets and draw conclusions. And so it's a really nice way to get people thinking about some of the things that teachers want you to think about, which is how do you plot data? How do you think about how you draw conclusions? And the nice thing is at the end, student participants can then choose whether or not they want to donate their data and be acknowledged in publications. So they're not forced to participate in a research program. They could be forced to do the activity just like you're forced to do any classroom activity or lab. But we're not trying to coerce them to contribute to our research program. But we're assuming that after doing the work, some of them might actually like to have that go out into the world and do something. And so we give them the option then of uploading their data tables, and anyone who wants to can be acknowledged later in publications. So we're at the beta testing stage right now. We've got our assessment in place. Some of the beta testing that we did this year in my classroom made us realize that scaling, so the photometry code works great with like 3 people troubleshooting at once. When we had 20 people running it at once, we crashed the internet in my classroom, let alone 50 or however big some of these intro astronomy classrooms can get. And so now we're trying to actually figure out ways to make it a little bit more user-friendly to avoid some of the memory issues we ran into. We were not anticipating that little hiccup. And that gets into that balance of finding the balance between authenticity. So what does research in astronomy really look like? It's not us putting our eyes to a telescope. A lot of it is computer programming and being user-friendly, because we don't want people to suddenly leave an astronomy classroom being like, I actually hate this science. It was very frustrating. We want you to give it, we want you to love it first and then frustrate you a little bit, but it's always that balance, right? And so we're anticipating some revisions and additional testing this year. If you are an instructor that's interested, we have a website that is up, but the form right now isn't really won't send you to me. So the best way to get a hold is just to email me directly. And I can talk to you after if you're interested. We did get some funding from NASA for a citizen science seed funding program. And so we've been able to hire a couple students to help us do the computer programming for this. This at the end is to catalog thousands of our yellow balls the same way we did for that initial 518 sample. And so getting the colors that the students would help us measure, and then using those to determine the physical properties like masses, luminosities, temperatures. And once we have that, then we can use it as a probe of star formation across the galactic plane, looking for differences and things like that. And one of the other exciting things here is that that data set then could provide a basis for machine learning techniques. And our goal here is that it would be really nice if we could look at an object and measure just its mid-infrared colors, and then use those colors to tell us more information about the physical conditions. Right now, doing things like measuring the mass and luminosity requires other wavelengths, emission lines. It's not easy. And so we're hoping that by getting a large data set, that we can actually find a shortcut by bootstrapping our way there. So. All right, and this, because I know somebody's going to ask it, how does JWST compare to Spitzer? Here's the side-by-side of the, so that the green emission, or the pink first off and then the green, the 8 microns, so the dust. This is what it looked like in Spitzer, where I was like, can you believe the resolution? And then, can you believe the resolution? So this is at 7.7 microns with Muri, the camera. Not a lot of side-by-side data out there yet because there's not a lot of data that's been released. And the stuff that's out there has all been the extragalactic look at all the very distant galaxies. But frankly, I am really excited about what JWST is going to give us for the interstellar medium. So. I just want to introduce the team of people too. So we've got Charles Curtin at Iowa State University, Grace Wolf Chase at Planetary Science Institute, and then this whole group of undergraduates at the College of Idaho that have contributed to this. So the C of I doesn't have a graduate program. All of my research students are undergrads. Only a handful of them are actually astronomy physics students. A lot of them are computer science students. And so I've really enjoyed having CS students on this because they can help me do the interactive clicking and all the data management. So I've got Riddick, Bezowit, and McKinsey. They're my most recent group, and 2 out of 3 of them have just graduated. So if you're looking for data scientists and training, McKinsey and Riddick I come highly recommended. And then we've been funded by NASA and the Murdoch Charitable Trust. So that was a lot to take in. So I'm going to leave my conclusions and takeaways up here while you guys have questions, in case you need a refresher. But just to get the high points, so if nothing else, if someone asks you what you learned tonight, there are thousands of yellow balls in the Milky Way, and most of them represent previously unstudied, so not yet studied sites of star formation. Follow-up studies is time-consuming to figure out their physical properties, but it's a really good fit to people-powered research. So the Periscope project was designed to let astronomy students contribute their efforts to our project. And the results from those efforts will answer questions about variations in star formation regions across a huge range of location and also size scale for stars. So I will leave those up, and now is a great time if you guys have questions. 8:30 on a Friday, so I don't blame you if you just want to.
Well, I was going to ask the James Webb question.
Yeah, I still have from you. Well, I had it originally in there as a hidden slide. I'll just put it there because it's really fun to look at. And then I thought, no, that's guaranteed. Somebody's going to want to know. So. That is. Yeah, I think that's intentional. I don't know much more than the average person about JWST's planning, but I think they probably were also trying to hit that pH emission band to trace the structure of the fine-grained dust in the galaxy.
The question I could ask is whether or not the team has put out a proposal to utilize Webb for targeting specific yellow balls that seem interesting.
That's the potential, the key word there for potential. Yeah, well, we're not working on the proposal, but it's on my radar, Erwin, in terms of like, yes, I think that when you're looking at thousands of objects, there's guaranteed to be some really good candidates for detailed follow-up study. The things that I would be looking for that would be any yellow balls. So these yellow balls, unfortunately, are not just nicely ball-like. I wish they were. There are some of them that show a lot more structure than others, which is also exciting because that means in some of these objects, we're starting to see they're down into the stellar content. And I think those would be actually some of the really ideal candidates to look at, because we might actually be able to see and discern individual stars. So I didn't say this, but I should have. A lot of these yellow balls are not just individual stars forming clusters. And so I tend to think of yellow balls as being more like a cluster of stars rather than an individual star. So James Webb would be really exciting for some of these objects where you're starting to actually see individual stars in them. But I haven't looked into the specs enough to know if that's feasible or logical or if somebody else is doing it. Yeah. Oh yeah, sorry. Yeah. Yeah. Right. Yeah, so the question is, there are thousands of these objects across the Milky Way galaxy, but that makes them actually kind of rare when you compare them to stars, where there's like billions, tens of billions, right? Hundreds of billions of stars. So yes, I guess it's kind of defined. It depends on your definition of a large sample size in astronomy. Compared to some of my colleagues who are looking at objects that number in the tens, I feel like we've got a lot to deal with, right? But yeah, I think that's a really good point in terms of astronomers, what astronomers consider a large amount of objects. And so for me, thousands is actually a pretty robust, you can do some statistics off thousands, but they're not as common as like stars. Yeah, it's a really interesting point. Yeah. So the question is if we've found yellow balls in other galaxies. It's a great question, and it's actually really hard. So what you run into there is that the resolution limit gets in the way. And so these objects for size scale for the yellow balls are a few tens of arc seconds across. And so if you were to try and look at these in other galaxies, they would be too small to be able to individually resolve. And so we're limited mostly by just objects in our own Milky Way. Great question. Yes, in fact, November 5th is the talk to come for that if I'm paying attention. Yeah, so the Dark Sky Reserve out by, out by Craters of the Moon, and Brian is absolutely the person to talk to about that. Catch him. I'm excited about that one.
Has anyone been looked at a yellow ball through like a spectroscope and take a look at the elements? I mean, you could probably tell us pretty close margin of error what those elements should be. Or has anybody done that? Or?
Not in detail. And so, sorry, the question was whether anybody has done spectroscopy towards these objects. So not in a systematic way. There's a lot of archival data that we looked at, looking at. So a lot of yellow balls are associated with known compact like dust clumps. And so the High Gauss survey, there was a lot of overlap between our sources and their sources. And a lot of those sources had been targeted for radiomolecular line imaging. And so we do have some of the sources that have emission lines towards them, but not in a systematic thousands of them way. Does that? But it's a great idea in terms of other avenues. There's one of the things I didn't have time to talk about, but that's a big part of this research. Because there's so much archival data out there of galactic plane objects, a lot of what we're doing is just cross-matching our work with other people's results to see for this yellow ball, who else has looked at it and what do they have for it? And so it's kind of in the era of big data, just combining data sets and seeing what falls out. Yeah, Sarah, yeah. So they're usually on average, so this is a whole section in the paper, on average about 1/10 of a parsec. So they're sub-parsec. But there is some variation there. And that was actually a thorny question because the citizen scientists who measured the radius of this thing, there's actually a lot of variation even with where you would say, well, where does it end. And so we did a lot of modeling with Gaussian. So we did a lot of fitting to see if we could kind of determine where the actual edge of the yellow ball is. But the short answer is about 1/10 of a parsec. Good question. All right.
Let's give Professor Devine a round of applause.
And I will put my email up here on the screen, unless Brian takes the screen down. Sorry, I have to go back through them. In case you want to reach out, especially if you are an astronomy instructor, you can send me an email if you're interested. And once we get past to making it a little bit more user-friendly, if you want to get in the line to use this, I'd be happy to incorporate you.
Thanks so much for coming out, everyone. Be sure to grab some flyers. We all have the free posters out there. If folks want to go to see the observatory, feel free to stick around the lobby and see her. Have a good weekend. Thanks, everybody.
Thank you so much for coming out on a Friday night. It's fun. Good job. His head snapped up with the word observatory. So. Oh, here.
Thanks for joining us, everybody. Have a good weekend. We'll see you on September 2nd when we have Professor Matthew Pasek come to talk to us about alien life.